As industrial designers, our first concern is with how people use products. We ask simple questions such as, who is using the product, what for and how? How can we combine a functional solution with an appropriate aesthetic? A new design opportunity has emerged as more products incorporate microprocessors. Designers must now understand the interactions between the user and the software, in addition to understanding traditional industrial design issues. This has led us to develop a new design discipline that we call interaction design. Industrial designers have always designed interactions between people and products. For example, a designer will consider the way in which a pencil is picked up and held, as well as the actions of writing or drawing. A modern business telephone combines a familiar interaction with many unfamiliar features. The simple operation of dialing offers no surprises for us. However, when additional buttons are provided for the control of specific features, most of us fail to use them because they are complex and unfamiliar. The design solution should express them to us in a way which is immediately obvious.
This cellular telephone for Dan call is differentiated from competitive products by the size of the display. As the cost of small displays comes down, consumer products like this can use them to give visual feedback.
Here is a sketch simulation of the user interface.
Scratch pad, messages, setup, telephone.
This idea for the design combines voice feedback with a display so that the telephone can be used while driving without the driver taking their eyes off the road.
Navgraphic Lorand for Trimble navigation.
The push buttons on this marine navigational instrument were all of fixed function when there was only a two-line LCD display. The next generation of the product included a large LCD display that could show graphics as well as characters. This allowed the use of soft buttons as well as constant function ones.
The screen design included fonts and icons. The borders around the window for plotting a course are inspired by navigational charts. A warning message is signaled by the image of a shark. Information is presented by a combination of words and pictures.
The interaction design process started with a thorough analysis of the sequences of operation of the navigation device, followed by the preparation of storyboards of screen contexts in rough conceptual form. The creative leap occurred when the first mock-up was prepared, which visualized the location and labeling of the soft keys, with different screens connected to each other side by side like tiles, and overlapping menus coming down from the top. This was refined in several stages to yield the final design.
Innovation strategy for Unisys. A group of application developers at Pac-Bell were studied. New design solutions were visualized to meet their future needs, both as three-dimensional products and user interfaces.
These storyboard sketches illustrate a user interface design for a future database application. The information can be organized in a series of pages like a book, so the turning of pages presents an image which helps to clarify how the product works.
A video editing system was used to animate the design and test its viability.
The users of Unisys equipment were also observed in banking applications. In this scenario, a customer called Chris Davis arrives at the bank. Existing database applications represent the customer as a long string of numbers, but this new design shows the bank clerk that Chris Davis has a face, a name and an address, as well as a bank account number. He wants to make an inquiry about a mortgage, so the screen representations of the forms which are needed are familiar to the clerk in the normal world of paper. If he wants to come back another time, an appointment book is represented on the screen with pages which turn, avoiding the unfamiliar interactions of electronic mail. When the right day has been found, the clerk puts Chris Davis into the book.
The system managers for tandem computers work in a world which seems abstract rather than familiar. They are used to interrogating screens of verbal information to help them trace faults in the system.
Our simulation of a new design approach shows a motif user interface environment, presenting the user with a situation where there are faults on 7 machines, color-coded here in red. One of several alternative views can be chosen. The system network view shows a map of the building with the network of the computers superimposed. The red machines appear to have no geographic relationship one with another. A Mackey diagram shows a schematic based on hardware connections, but again the red machines are randomly located. The logical diagram based on software shows that the source of the problems lies with TCP number 15A, that is Terminal Control Process number 15A.
Claris was founded by Apple as an independent company to develop software. Their first product was MacWrite 2, for which we developed screen graphics within the Macintosh environment.
The designs for the packaging gave us a direction for the visual identity of the screen icons, for which these are sketch alternatives. Each icon was designed in a magnified view to smooth out the lines and create a loose and informal appearance. An animated splash screen was created to help fill the time gap after the desktop icon's been selected, while the program is being recalled from memory.
This infusion pump designed for Kendall McGaw delivers drugs to a hospital patient intravenously. The accurate use of the controls can therefore be a question of life or death.
A fully operational interactive simulation of the design was prepared which could be tested by nurses, with several iterations being developed very quickly in response to user evaluation. The simulation uses a scanned photograph as a background, with a paint image constructed to give a life-sized front view of the product. A prototyping program provides the interactivity so that the behavior of the machine can be demonstrated and developed before any software engineering effort is started.
To redesign the Microsoft mouse, our industrial designers made models of many different shapes. Our engineers built 4 working prototypes, and our human factors people performed a series of user tests. The tests allowed direct comparison of time and errors on specially designed tasks, which we programmed with HyperCard.
Fit's tapping task measures the trade-off between speed and accuracy for the most common mouse usage, that is, move and click. With this maze, we were able to show a significant performance advantage for having the ball at the front of the mouse and not in the back. This task requires the ability to hold the mouse still while clicking and shows the advantage of buttons on the top and not on the side. This task requires repeated short strokes with the button down and then up. This is difficult with trackballs where the buttons are hard to hold while rolling the ball. This task requires typing, then pointing, then typing again and again. It measures homing time as you move from keyboard to pointing device. Surprisingly, the mouse does just as well as devices with fixed positions. These laboratory human factors tests allow rapid exploration of a wide range of design parameters.